Projectile motion. In exercises 71 and 72, consider a projectile launched at a height h feet above the ground and at an angle theta with the horizontal. So you can see the diagram here. You've got a baseball player hitting a baseball over home plate, and the ball leaves after being hit at an angle theta with the horizontal. If the initial velocity is v naught feet per second, the path of the projectile is modeled by the parametric equations x, meaning the distance it has traveled horizontally from home plate, is equal to v naught times cosine of theta times t, where t represents time since the baseball was hit, and y, which would represent the height of the baseball above the field, is equal to h, which is the initial height when it was hit, plus v naught times sine of theta times t minus 16t squared. So the center field fence in a ballpark is 10 feet high and 400 feet from home plate. So this is the fence for the park. It's 10 feet high, 400 feet from home plate. The ball is hit 3 feet above the ground. It leaves the bat at an angle of theta degrees with the horizontal at a speed of 100 miles per hour. So the first thing that we have to do for part A, where it says write a set of parametric equations for the path of the ball, is look at the instructions in bold where it's telling us what the parametric equations should be, but be careful to note that the initial velocity has to be in feet per second. So you have to begin by converting 100 miles per hour for the initial velocity into feet per second. So multiply 100 by the conversion factor, 5,280 feet are in 1 mile, and then multiply that by the conversion factor, 1 hour has 3,600 seconds. And that would give you the initial velocity to be 146 2/3 feet per second. So 146.67 is V naught. So if you look at my parametric equations that I've entered into Desmos, and in Desmos, you enter a set of parametric equations as an ordered pair. So the ordered pair has the parametric equation for x, comma, the parametric equation for y. So if you look over here in cell 1, here's what you see. So you have V naught, 146.67 feet per second, times cosine of theta. I'm using degrees. You can do that in Desmos by clicking on the wrench symbol and going to degrees here. And I'm using 15 degrees because I'm doing part B. Use a graphing utility to graph the path of the baseball when the launch angle is 15 degrees. Is the hit a home run? So we'll think about the question in a little bit. But I'm using 15 degrees because I'm doing part B. So I have x is equal to 146.67 feet per second times cosine of 15 degrees times t, as you can see here, comma, the parametric equation for y is the height at which the baseball was hit, which is 3 feet above the ground. You can see that in the diagram as well. So we have 3 plus v naught, 146.67 feet per second times sine of the launch angle, sine of 15 degrees times t, minus 16t squared. So now I have entered my parametric equations into Desmos, and t is equal to 0 is when the baseball is hit. T is equal to 2.5 would be 2.5 seconds later. So now you can see that Desmos will go ahead and graph it. So you can see the graph here representing the path of the baseball. And if you copy the set of parametric equations and paste and change the parameter from t to a and add a slider, you can see the actual movement of the ball. This is how the ball is moving, as you can see by the green dot moving across the screen. And it hits the ground. And if you click label here, you'll also be able to see the coordinates of the baseball's position above the field. where the x coordinate tells you how far it has moved horizontally from home plate, and where the y coordinate tells you the height of the ball above the field. And of course, at 2.5 seconds, it would actually be on the ground. It can't really go below the ground. So the ball hits the ground a little bit before 2.5 seconds. So if I try to move it just right, I can see that it's going to be maybe around 2.45 seconds, or a little bit before that, a little bit before 2.45 seconds, somewhere between 2.44 seconds and 2.45 seconds after the ball was hit, it would hit the ground. So now we're going to take a look at the question in part B. It says, use a graphing utility to graph the path of the ball. So we've done that when theta is equal to 15 degrees. Is the hit a home run? So how do we answer that question? Is the hit a home run? So we know that it says here that the center field fence in a ballpark is 10 feet high and 400 feet from home plate. So for it to be a home run, it has to go 400 feet of horizontal distance from home plate. And after it has gone 400 feet horizontally, it must have a height that's greater than or equal to 10 feet. Otherwise, it's just going to run into the fence and be on the inside of the park and not be a home run. So that doesn't happen because you can see that when the baseball hits the ground, the horizontal distance from home plate is less than 400 feet. It's about 345 feet. So 15 degrees, that's not going to do it. It's not going to be a home run. So now let's go ahead and take a look at part C. Part C says, use a graphing utility to graph the path of the ball when t is equal to 23 degrees. Is the hit a home run? So I'm just going to go back to cell 1 and change my angle from 15 degrees to 23 degrees. So we want to change the angle from 15 degrees to 23 degrees. So I'm doing that. Now I want to do the same thing for cell 2. So change the angle from 15 degrees to 23 degrees. Having done that, now I have a different path, but it looks like I need to increase the time from 2.5 seconds. It stays in the air longer. So maybe I'll change it to 3 seconds. Still above the ground, but maybe I'll change it to 3.2 seconds, 0.3 seconds, 3.4 seconds, 3.5 seconds. So 3.6 seconds. It's almost at ground level again, maybe 3.65 seconds. And it appears to hit the ground sometime around that time. So the question is, use a graphing utility to graph the path of the ball when theta is equal to 23 degrees. Well, you see the path of the ball there. It's in red. And the question is the hit a home run? So we know that center field fence is 400 feet from home plate and 10 feet high. So let's go ahead and do this. So we're going to write x is equal to 400. That tells you how far away from home plate we are. So this is 400 feet from home plate. That's where the center field fence is. We also know that the center field fence is 10 feet high. So I'm also going to graph y is equal to 10. The center field fence is 10 feet high. So you can see that you can see what's going on here. As the ball is moving, it starts here and then it's hit and the ball goes up, up, up. It reaches a maximum height, and let's see if we can pause it right about there. So take a look at this particular point here. When it has gone a horizontal distance of about 400 feet, when it has gone a horizontal distance of about 400 feet, you can see that the height of the baseball is about 32 feet above the field. So it's going to clear the fence because the fence is only 10 feet high. So it will, in fact, be a home run. So we've done parts A, B, and C. And in part C, use a graphing utility to graph the path of the ball when theta is equal to 23 degrees. Is the hit a home run? Yes. So if you wanted to do some additional work to label the coordinates of the baseball's position above the field at certain times, you can do that. You can see in cell 4 that I have entered values for B from 0 to 0.5 to 1 all the way to 2.5 seconds. You can copy the set of parametric equations from cell 1 and paste and change the parameter from T to B, but I would have to change the angle as well to 23 degrees. And when I do that, you can see the certain positions of the ball as a function of time. And maybe I want to go not just to 2.5 seconds, but to maybe 3.5 seconds. And there you see that. And if I wanted to label the coordinates of these points, I can do that. This just tells you where the ball is as it is flying over the field at half-second intervals of time. But that's not necessary for you to do the problem. And we did parts A, B, and C of number 71.